So most of you probably haven't noticed, but I just put in the grids for the first test as well as the solutions. So if you go to that module where I put the exam one prep materials, you will also see the solutions in there too. There were a few things I wanted to talk about, so I'm going to go ahead and share the test. Just go over a few things. While I'm doing this, if you have any specific questions, please go ahead and stop me. Like I said, if I don't get any questions from people, I'll just go ahead and focus on the things that were common that stood out to me. Otherwise, we can go over some things in more detail. All right, so this true or false section, let me zoom in a little more. Mostly went pretty well. I think the last two were probably the most commonly missed, if I have to guess. Remember with D, if you were to just integrate this or find the antiderivative and plug in the 5, plug in the 0, it's going to look like it converges. But the fact that there's a discontinuity with this function on the interval means you have to split that integral up into two smaller integrals, and neither one of them converges. E actually comes out. So if you were to set up the first step in integration by parts, then that is an acceptable first step. If you choose u equals t squared and dv equals e to the t dt. On question 2, part A went mostly pretty well. The most common mistake I saw there was that people were basically subtracting the functions in the wrong order. Since the only way to get a single integral to do this is to set this up in terms of with functions in terms of y, which I've already given it to you in. But the red curve, the parabola on the right, needs to be the one that basically is going to be red minus blue. You want to subtract the greater function minus the lesser function, and greater in this circumstance means further to the right. B mostly went pretty well. The most common thing I saw was that a couple things actually. The derivative of negative e to the x is negative e to the x, and I think I saw a lot of people dropping that negative sign. And I saw a few people either making a mistake on transforming those limits of integration or just forgetting to do it. C was by far the most missed question on here, and I'm not really surprised that it was. These work problems where you're basically pumping a liquid out of a tank these are pretty tricky. I'm not going to go through it in too much detail right now, but I would encourage you to consult the solution on that one that I posted. D, most people did really well there. 3A was mostly answered correctly. 3B, not quite as commonly done, and then same with C. And I think, yeah, I was actually kind of surprised about that. The fact that so many computation errors happen with C. I think most people tried to compute the integral that they got for A because I think it seemed a little more straightforward to do, but really either one of them should give you the correct answer. All right, 4. And the most common thing I saw, and I think only a couple of people did this correctly, but really the first thing we have to do with this function is to perform this division. The degree in the numerator is bigger than the degree of the denominator, so you do need to perform that division. And most people I saw just went straight to, substituting in this factored form here and setting up those three smaller fractions, those three smaller rational functions, which you actually can't get the correct values for A, B, and C doing that. You do need to divide first. The trapezoidal rule went really well, even for people who didn't do A correctly. And 5 overall went really well. If one of these was more commonly missed than the others, it was B. A few people didn't realize that integration by parts is the way to go there, or just had an error doing that. But overall, 5 went pretty well. So I have put like I said, I put the grades in, so go take a look at those. You can even take a moment to do that now if you want. I just put those grades in, so I doubt most of you have seen those. Just a few quick stats on those. If you look at your test, basically, if you go to Canvas, for most of you, those of you who submitted a PDF, I was able to actually take notes on that PDF and then upload my notes to as a response, as a comment on your submission on Canvas. So if you gave me a PDF, I was able to actually annotate and send those back. You'll see a score out of 80 on the front of the test. And if you add 7 to that, that will be your score that's actually in the grade book. So the average raw score, or I guess after that 7-point scaling, the average on this was a 78%. And the low was low was 43 out of 80, and high was 77 out of 80. If you have any concerns, please let me know. So because office hours are a time for, it's open to everyone, I do not want to use that time to discuss your test with you on an individual basis. So if you want to talk about your test individually, send me an email. Let me know a few times that you're available to talk to me, and I'll work with you to schedule a meeting. Any questions about the test before we move past? Okay. So we've got chapters 5, 6, and 7 behind us. We're going to get into chapter 8 now. Really, there's only a few sections in 8. We're only going to do the first 2. Okay. So the first section we're going to look at in chapter 8 is all about arc length. And before I get into it, and like I said, this has happened before, can someone confirm that they can hear me? And also would like to confirm that, okay, so I can hear you all. All right, good. So let's get into it. So we're going to be talking about arc length, which is probably something you've done in relation to circles before, but now we're going to generalize that so we can find the length basically along any curve, along any function. So let's build up to that. So go ahead and start this. So the rationale is basically this, and we'll go through this in a couple different ways. I want to take this pink or this blue curve here, and I want to break my X interval into all these little subintervals, which is something we do with area and volume as well. And for each one of these, what I would like to do is basically approximate the length as closely as possible with these straight line segments here. So something that we've done with area is when we take this partition, these subintervals, basically what we are typically doing is just assuming a constant value over these intervals. And basically representing that constant value with a horizontal line segment like this. So if you remember back from geometry, you probably saw arc length represented as S. So let's say I wanted to find the arc length here from A to B. So it's going to look really simplistic, but we're actually just using this kind of as a motivation to build up on it. So let's say we're just going to go the old approach, like kind of like we do with area, where I'm just going to take all of these little subintervals, and all I really care about is that separation in X. So all these are going to be little dx wide intervals. Then basically what I am integrating is nothing more complicated than dx. So if I integrate dx, I'm going to wind up with this antiderivative x evaluated from A to B, and that's just going to be as simple as b minus a. So if we try to apply this, horizontal line segment, constant value approach to arc length, I mean, we're obviously not going to have a very faithful look at this. The arc length along this curve is certainly not equal to b minus a. So this is a bad approximation. We need to look at something a little more sophisticated to represent arc length. All right, so, and really what we would like to do instead is, we have a continuous function here modeled with this blue curve. And if we partition the x-axis into these, finitely many intervals that have equal width, then what I'm going to do instead is, yes, I have to worry about the change in x, that dx. But if I'm going to represent arc length faithfully, as accurately as possible, then I need to be worrying about this change in y as well. So I'm going to have some change in x. I'm going to have some change in y. And then basically that small change in x and that small change in y, I can use those two pieces to get this ds here. So first question for you on this: how is ds related to my dx and dy?
Is it like dx squared plus, so is it this, is it dx squared plus dy squared is the square root of ds?
Yeah, so yeah, I mean, this is a right triangle. I can absolutely just think of this as, this is a direct application of the Pythagorean theorem. So ds is equal to the square root of dx, so dx squared plus dy squared. So that's good, but what I really need to do, I mean, you're probably suspecting, rightfully so, this is all leading up to an integral, and right now I'm only able to deal with integrals that are written in terms of a single variable. So I have a problem here. I got dx and dy. I really need to get that down into one idea here. So next thing I want to do is, we're more naturally, predisposed to looking at x as our independent variable. So let's try to build up to that. Is there any way I can relate dy to dx? Make a little room here. Specifically, do I know what this slope is? Or can I represent it in terms of things that in terms of these quantities that I'm already looking at? What's the slope of this straight line, this pink line?
dy by dx.
That's dy over dx. So I'm going to write something here. It's going to look maybe a little bit simplistic, but that's okay. I know that dy is equal to dy dx times dx. I mean, symbolically, you can kind of see why that's true. You can kind of visualize the dx will cancel so the dx divided by dx, that'll just cancel to yield 1. So yeah, dy equals dy. I mean, it looks pretty simple, but let's talk about, you know, in terms of differentials, what does this mean? And really, this is just a representation of the slope that I have marked over here. If I have some change in x, which I'm calling dx, I can multiply that by dy dx, which is a slope that I'm assuming is constant on any one of these intervals. If I multiply that by dy dx, then I'll get my change in y. So I'm going to rely on this to rewrite or to re-express this this ds. So I'll go ahead and make this substitution. ds is equal to the square root of dx squared plus this thing, dy dx squared times dx squared. So still got that variable in there. So let's still have that second variable in there. Let's keep on going here. I'm going to factor because I have a common dx squared term. So this is the square root of dx squared times 1 plus dy dx. Some room. And this is going to be pretty crucial for this entire section. So if anybody has any questions about the way I'm building this up, please stop me. From here, I have basically 2 factors multiplied together, and they're both contained under a square root. So I can rewrite this like this. I'm going to go ahead and have them switch positions. So 1 plus dy over dx squared times the square root of dx squared, which this just becomes this, ds equals square root of 1 plus dx squared times dx. And if I rearrange that a little bit further, basically now what I have is ds dx. And just to kind of help us orient all this stuff we've done, let's go remind ourselves what S stands for. S is a measurement of arc length. Now, basically, if I could take this curve, this function graphed in blue, if I could take that and stretch it out and just take a simple measurement of it, that's the length I'm going to find. So I have ds dx equals this radical. I know that, so basically this is the rate of change of arc length with respect to x. I guess really I could do this at either place, but I'll go ahead and integrate both sides of this one and move it down here. that gives us this idea. S is equal to the integral, and integral over some interval, just call it A and B, of the radical 1 plus, and I'm going to rewrite this using a different kind of notation, but really it's so in general, we're going to think about our arc length like this. So we're integrating over some area or over some interval, the square root of 1 plus f prime of x squared. So like I said, we're going to be using this quite a bit. So it's a pretty important idea. If anybody has any questions, please let me know before we go on to actually taking advantage of this. All right. So let's go ahead and use this. We want to find the length of the arc along this curve, y squared equals x cubed, between these 2 points, 1, 1, and 4, 8. So just to kind of remind us what we're working towards, I know I am integrating over some interval. This idea here. So for this first one here, let's try to set this up so y is a function of x, and I want to use x as my independent variable. So if I want to write y as a function of x, let's rearrange. What is f of x equal to?
Square root x to the third.
Yeah, so square root of square root of x to the third, or just to make this a little more conducive to all the calculus we're going to have to do, we can also rewrite it as x to the power of 3/2. Okay, so we have our function. Basically, we've represented this curve as a function of x. So in order to find the arc length, what should we do next with this function of x? What was that, Mona Lisa? I'm sorry.
Do we find the derivative?
Yep, let's find the derivative. So, the f of x is equal to x to the 3/2. If I take its derivative, I should get 3/2 x to the 1/2, or 3/2 radical x. And we're getting there, but in order to use this arc length integral, I also need to know what this is. And this will come out to 9/4x. So now I think I'm okay to start setting up this integral. I'll leave the limits off for now, but I'm integrating 1 plus 9/4 x dx. And what limits should I use here? What makes sense for my limits of integration?
One and four.
1 and 4. So I am using x as my independent variable, so it makes sense that my limits of integration are written in terms of x. All right, so our integral has been set up. So how do I deal with this integral?
Would it be u substitution?
Yep, we can try that. What do we want to use for u?
One plus 9/4 x.
Yep, so we've got a composite function here. Try this. And that means that du is equal to 9/4 dx. Or that dx is equal to 4/9 du. So we can start using that to transform this integral in terms of u. What are my new limits going to be on this integral? If I do this correctly, is that the upper one should be 10 and the lower one should be 13/4. So I'll go ahead and pause here for a beat because really this we're almost done. I mean, we've set up the integral, we've used substitution to make it a little easier to handle. But unless there are any questions, I think we're ready to go ahead and compute it. Right, so the antiderivative of u to the 1/2 is 2/3 u to the 3/2 from 10 to 13/4, or 13/4 to 10. And this, collect these, get 8/27. And if anybody wants to approximate this, they can, but we can just go ahead and leave it exact. So anybody have any questions on this first one? All right, let's go ahead and keep going. All right, so I'm going to set up the integral to find this length. So just to show that we can handle both approaches here. So far what I've given you is that, the arc length is equal to this integral. So the integral, and I'll be really explicit about this, x equals a to x equals b of this radical 1 plus f prime of x squared dx. But there's no reason you can't express this in terms of y. In fact, for this example here, it probably makes more sense to do this in terms of y because you already have a function where x is equal to some function written in y. So, I mean, obviously for this one, it wouldn't take much doing to re-express this in terms of x, but let's just keep what we have. So I have a function. I have a way to express x as a function of y. So I want to set up the integral to find the arc length. So where should I go from here?
Find the derivative of that.
Okay, good.
F of y.
So f prime of y is equal to 2y. We know that we'll have to square that. All right, and now what?
Just set up the integral.
Okay. So the integral from, I'll let someone describe the limits to me. But I'm integrating 1 plus, or the radical 1 plus 4y squared dy. And this one, it's what's a little hidden is, the x limits and the y limits would be the same, but really just focus that we're really interested in these y coordinates, since y is our independent variable. So we're going to go ahead and stop here. This integral gets complicated really quickly, but I think the more important thing for right now is to just set these integrals up. Any questions here? All right, let's keep on going. All right, so I want to set up this integral, set up the integral for this arc length. So I'll let you all drive. What should I do to start?
Set the function correctly.
Okay.
Where it's like y equals 1 over x.
Okay. So y equals 1 over x. So we have a function written in x. So that's good. Definitely a good first step. Now what?
Derivative of 1 over x.
Okay. So we'll take a derivative of 1 over x. Might be helpful to do this. X to the negative 1. Gonna have to square this. All right, now what?
We set up the integral.
So I'm integrating from where to where?
One to two.
1 to 2, because we were looking at x coordinates. And this is a little bit on the optional side, but we can do a little bit of rearranging. All right, any questions here? All right. How about this one?
Can we rewrite it?
Rewrite it in how so?
Just I'm sorry, like e raised to y.
Oh, so you want to solve for x? Okay.
Yeah.
So let's try that. So y equals natural log of secant x. We start trying to invert this, we'll get e to the y equals secant x. And then x equals inverse secant of e to the y. So I think this would work. I don't know if we have any yeah, the integral of the inverse secant is something that's already making me nervous. So let's keep this on hand, but let's try to do this with x as the independent variable first. So keeping this with x as the independent variable, how should we start?
You find the derivative.
Okay, so let's find the derivative here. So f prime of x, what is the derivative of the natural log of secant x?
Is it 1 over secant x?
Definitely at least contains that. So yeah, the derivative of any natural log is going to be
Oh yeah, 1 over sec x, and the derivative of sec x is sec x tan x. So
yeah, it's one of these derivatives that looks kind of scary, but once you start breaking it up into smaller pieces and invoking chain rule, especially this one becomes really simpler than you might think. And that simplifies to tangent x. All right. So definitely a good piece of evidence there. Now what?
Square it.
Right. So from there we have squaring this. Tangent squared. And now we can start setting up the integral. So integrating from 0 to pi over 4 of 1 plus tangent squared x dx. Can we do anything else with this?
There's this integral of sec theta, which is log mode sec theta plus tan theta.
So this ends up being the integral of secant. So let's build it up a little bit. 1 plus tangent squared, that is simply secant squared. Then we have this integral of secant x, which
It could be two forms, log mode of x plus square root of 1 plus x squared, or log mode of sec plus tan x.
all right, this is the one I remember. And yeah, like I said, this is not something I'll be expecting of you on tests or anything. It gets complicated pretty quickly, but I posted an article on why this is the case on Slack if you want to go take a look. So evaluating that from pi over or 0 to pi over 4. So natural log of secant pi over 4 plus tangent pi over 4 minus the natural log of secant 0 plus tangent 0. All right, so what is the secant of pi over 4? Just a reminder, secant is related to what other more familiar trig function? Mona Lisa, you're pretty quiet today. You might want to turn your microphone up.
Square root of 2.
Right. So this is 1 over cosine pi over 4. So yeah, that ends up becoming square root of 2. So natural log of square root of 2 plus 1 minus the natural log of secant of 0 is 1. Tangent of 0 is 0. So this term goes to 0. So we just get the natural log of radical 2 plus 1. Any questions there? Went a little bit further with that one than I intended, but that's okay. All right, something else that's good to do with arc length. So the last few examples we did, we just basically we just found the arc length or set up the integral to find the arc length over some fixed interval. But now what I'd like to do is basically write a function for the arc length. So in this case, I'm not trying to find a number. I am trying to find a function. But really the process, I mean, there's a lot of commonalities here. So basically I want to find the arc length from 1, 1 to generalized XY, some other point. So I'm dealing with arc length. So how should we get started? So we know we're going to need a derivative. Let's go ahead and take that. So it'll be 2x minus 1 over 8x. So now that I have this derivative, what should I do with it next?
Square.
Go ahead and square it. All right, so I took the derivative, squared it. How about now? Actually, I'll go ahead and take over here. So we're looking for a function. So instead of just calling this s, I'll call it s of x. And I want to integrate from 1 to whatever x I want. So I'm trying to get a function here that will basically give me the arc length from x equals 1 to whatever x I want. And the thing we are going to integrate is 1 plus 4x squared plus 1/2 plus 1 over 64x squared dx. And I think I have an error somewhere. Definitely do. Yep, right here.
Wait, isn't that the same as 2x plus 1 over 8x? Well, plus
Yeah.
1 over 8x the whole square?
Yep. So yeah, that's why that's how I knew I had an error. But basically, yeah, if you're okay with basically, if you take note of what happened when I squared 2x minus 1 over 8x, I got this trinomial here. And really, the only difference with this trinomial I have under the square root now is that I'm adding 2x and 1 over 8x. So the fact that this is a perfect square really helps me out. So this is 2x plus 1 over 8x squared dx. So this is the integral I have from 1 to x of 2x plus 1 over 8x dx. And I just realized that I should not be using x for any of these variables. I'll explain why that is in a second. Or does somebody know why that's a problem?
Is it because x is like in the bounds?
Yeah, so basically, when I have x, when you have your bounds on your integral, those things are basically constants. So I don't want to have x fulfilling two roles. Basically, when it's the bounds on when x is the bounds on a variable, we're treating it like a constant. I want to integrate this function for every value between 1 and this maximum value, which I'm calling x. So that x is a constant. But when I have x inside the integrand, it's a variable. So I really cannot be using x to do both those jobs. So I need this this intermediate variable t to integrate in the meantime.
Would it
So
be s of t instead of s of x?
I'm sorry, what was that?
Would it be s of t instead of x of x too, like for the integral?
No, and I think you'll see why when we integrate here. You know what? Let me get to that question after we deal with this integral. Because the fact that we have, you know, our independent variable as one of the bounds here doesn't really change, you know, that we still have to take an antiderivative and evaluate that antiderivative at both limits. So this antiderivative becomes t squared, and 1 over 8t is 1/8 times the natural log of. I'm going to leave off the absolute value since this is, oh, this function is not defined for negative numbers anyway. So now let's see what happens when I evaluate this function at the limits. I get x squared plus 1/8 times the natural log of x minus 1 squared plus 1/8 times the natural log of 1. This is 0. And then what I end up getting here is a function So I have a function here whose independent variable is x. So basically, using t inside that integral was really a means to an end. But the fact that I had x as my upper bound for that integral, I knew I was going to end up with what I wanted, which was a function whose independent variable was x. So before we go past this, what does this function represent now? What does s of x represent for us? Actually, let's give an example here. Let's say I use this function to find s of 10. We could definitely, you know, plug in 10 and get a number, but what I'm more interested in is what would s of 10 represent? What would that tell us?
would it be the arc length from 1 to 10?
Yep, that's basically it. Yep. So the arc length over the x interval. One, 10. And that was what I was not wanting to get lost was, you know, when this function we have set up, it's kind of, it might be a little bit lost that what's really baked into this function is that we're starting with an x value of 1. And so just a kind of a quick check here. You know, s of 1 better equal 0. Because if I really did this function correctly, then the arc length from x equals 1 to x equals 1 should be nothing. And I think if you plug in 1 to that function, you'll see that fits. So any questions on, you know, using this to build a function? All right, got one more. All right. Our last one, so I'll let you all drive. How should I start?
Find the derivative of the function.
Yep. So let's take a derivative. I'll go back to this notation. So 2 times 3/2 times x to the 1/2. So I got 3 radical x. We're going to need to square this thing. All right, good first couple of moves. Now what?
Set up the integral from 1 to x.
Okay. So our arc length function is going to be based on an integral from 1 to x of, and what's the integrand?
Square root 1 plus 9t.
There you go. Good catch. Yeah, don't make the same mistake I did. But yeah, we want to use basically any other symbol, but t is pretty universal. All right, so got our integral set up. Looks really good. Now we have to deal with this integral. So how do we make this happen?
Use substitution.
Yep. So it goes use substitution. This looks a little bit familiar from earlier, so we're going to handle it in a lot the same way. So u equals 1 plus 9t, du equals 9 dt, dt equals a 9th du. And for now, what I recommend we do is let's treat this as an indefinite integral. Just because, you know, our upper limit is already unknown. It's already a variable, so just setting it up in terms of some other variables, I recommend just treating it, just doing this as an indefinite integral and then back substituting. So from here, I'm going to transform my integral of 1 plus 9t dt into 1/9 times the integral of u to the 1/2 du All right, I'm gonna go ahead and push forward unless anybody has any questions. But now that I have that antiderivative, I can evaluate it at these limits that I set aside. And go ahead and double check me, but I'm pretty sure that's good.
How come you put 10 in on the second part?
That's a good question. How come I did put 10 in there?
Oh, the 1 plus 9. Okay,
Yep.
yeah.
Yep. And that's one thing I also wanted to point out from the test. I saw a couple questions, and off the top of my head, I can't remember what questions they showed up on, but I saw a couple people run into the trap of just taking for granted that what happens at the lower limit comes out to be 0, which is, it happens a lot, but it definitely something you have to check. All right. I'm gonna go ahead and get out of this. Keep the annotations. All right. So that was section 8.1. Like I said, we're only going to be dealing with the first 2 sections from this chapter. So the other one is, so we did the volume of a revolved surface. Now we're going to do the surface area of those solids of revolution. So just like with the arc length, I'm going to go ahead and develop this a couple different ways. So, you know, this thick blue line on top here, or this blue curve, this is our generating function in 2 dimensions. Then when we revolve this around the x-axis, we're going to have a 3-dimensional shape. So like we usually do, let's split this up into not going to draw all these in, but let's partition the x-axis. So basically what we're going to have is this, and these are, you know, made these pretty thick, but that's okay. So let's just go ahead and just color in one of these. So basically what I want to find is a surface area. So if I were to take one of these, and really I'm gonna go ahead and delete the shading because I don't really care about all the shaded area. I really just care about what's happening at the outer edge. This is surface area, not volume. I don't care about the inside. So I'm just gonna kind of darken in this top edge here. So if I were to take that top edge and revolve it around the x-axis, what kind of shape am I making?
A cylinder.
The cylinder, well, part of a cylinder, specifically what part of the cylinder is it?
The side of it.
Yeah, it's what we've called before the lateral surface. So the area of lateral surface of the cylinder. So if I want to find that area, I'll call it capital S, capital A, so we don't confuse it with two-dimensional area, planar area. So let's say this is a dx wide interval. So I want to find that area along that surface of the cylinder. So I know that dx is going to be part of that calculation. But what's going to be the rest of it? How am I going to find what else do I need to introduce to this to find that actual area? Let's amplify this a little bit. I know this thickness is dx. So really, the other missing piece I need is, how long is this, if I were to stretch this out, how do I find this length? Think about the way we found that when we were talking about volume cylinders. It really is no different from the way you find this length now.
Isn't that pi r?
Very close. It's 2 pi r.
Oh, the full length. Okay. That's
Yeah,
the
yeah.
pi.
Because it's the the circumference around the circle. So basically, let's say I just took a point. If I just took a point and wrapped it around the x-axis, then that's a circle. And since I'm only worried about the distance along the outside of the surface, that's a circle. That's the circumference of a circle. So because of that, what I'm looking at here is this integral from a to b of 2 times pi times radius times dx. But the way I set this up, how can I express the radius in terms of the functions I have here?
This is f of x, right?
It's just f of x. So and now that we have this, unfortunately, I'm going to tell you to, take this with a grain of salt. So this right here, I'm assuming that basically just like the last time we did arc length, I'm assuming that a constant y value over any one of these intervals. So what we're going to see soon is that, this is a not good enough of an approximation. So we got to do something a little more sophisticated than just taking these constant values and just setting these up as cylinders. So we're going to use this to build up to something a little more accurate. So again, we're going to partition this this interval into several smaller intervals. But just like we did with arc length, if we want to get a really faithful representation, I don't want to do horizontal line segments. I'm going to do still linear lines, still line segments, but they're going to more closely resemble the shape of the function. So are we clear on what the difference is that I'm doing? I'm sorry, I'm going to mute myself for a second and come back. All right, let me go ahead and restart this again. Okay, so again, the big difference in the way we're approaching it this time is I am, rather than just taking a horizontal line segment, what I want to do is, you know, mimic the curvature of the curve. So let's work with this interval here and wrap it around the outside of this curve. So now instead of a horizontal line segment, I can really truly connect these, and the area of the surface I'm looking at is here. So I'll ask, what kind of a shape is this? But it might not be as obvious. So we were dealing with cylinders before. What shape is this now?
Shape is what?
This like this
Oh, that's
shaded.
that's a frustum, right?
Yeah, it's a frustum. And in case you need a refresher on what that word means, basically, if I were to extend this out to the left, I would have a cone. Because if I were to extend it to the left, it would eventually taper to a point. I am not going to do that because I'm only interested in what happens over a given interval. So really what I have is a cone with a cut made that's parallel to the base. And that's what a frustum is. A frustum is a cone. You take a cone and you make a cut that's parallel to the base. So basically you have two circular bases of different sizes and, you know, some height. In this case, the height's going to be dx. So from our first attempt, we had this approach. So the integral from a to b of, you know, 2 pi times f of x dx. So we're upgrading this integral from a to b. We still want 2 pi times the radius. But what's going to change now is this. Because I'm no longer assuming just a horizontal change in x. Now what I'm assuming is, something that more closely mimics the curve. So I'm going to replace that dx with ds. So instead of having my differential term be just some change in x, I want my differential term to be a change in the arc length. So that's the motivation. But in terms of actually computing these things, we can't really do, I have a function written in x and a differential term written in s. I don't know how to do integrals that work like that. So eventually what I have to do is express ds in terms of x. But luckily, we just spent a section doing that. So I'm going to go ahead and box both of these in because they both have their purposes. So the top one is not really good for making the computations that we're about to make, but this is really what we're doing. This is this conical frustum approach. So you have your 2 pi r in here, which is the circumference of a circle. And if you multiply that by this arc length, which is just a one-dimensional length, you're going to get an area. So just to put some more details in there, 2 pi r, this is a circumference, which is a length, and that is a one-dimensional measurement. So when I multiply that times ds, that is a length times a length, which is an area, and that's a two-dimensional idea, which is surface area is what we're after. That's basically a two-dimensional measurement on a three-dimensional object. So I'm going to stop here. I know that this development is probably a little mysterious right now. So if you have questions, this would be a very good time to ask them before we actually start using this to make computations. Okay, so let's go ahead and start some examples. All right, so this curve, so this is actually part of a circle. So let's draw a graph to get ourselves oriented. So this is a circle of radius 2, centered at the origin. And really, we only care about this from -1 to 1. And really, we only care about the so we're going to take this more bolded edge here, and we're going to wrap this around the x-axis. So this is our first approach at this. So I'll go ahead and remind you of this integral. And for now, I'm going to leave the function notation out of it. Let's just call it what it is. Basically, you have your circumference. So I'm going to call this 2 pi r. Highlight that this is really a circumference. And we're going to multiply this by ds, which is a small change in arc length. So if I'm revolving this around the x-axis, and really I'm only interested in this part of the curve, is the radius what's the radius going to come from? How can I express the radius in terms of the functions that I have? Probably worthwhile if I actually put a dx strip in here. What's the radius of this strip that I just drew? So hopefully hopefully people are thinking it, but the radius in this case is just as simple as y. I'm using dx intervals, so I am going to set this up as with x as my independent variable. So do a little more rewriting here. From -1 to 1 of 2 pi times the square root of 4 minus x squared ds. And just to remind you, how do we find arc length? Arc length is ds is equal to 1 minus this derivative squared dx. So our next job here is to
Isn't ds 1 plus, not minus?
absolutely is. Thank you. All right, so now we have, let's pause here because we need to figure out what f prime of x is. So how do we deal with f prime of x? So we take the derivative, we have to involve chain rule here. So you get 1/2 times 4 minus x squared to the -1/2. Then you need the derivative of the inner
2 sine
function.
theta.
What's that?
Is it 2 sine theta?
We're not going to involve a trig substitution here. Though I think you're right that you could. And the reason we're not going to, hopefully, will become apparent in just a second, but a lot of this simplifies nicely. So here's our derivative. I'm actually going to pull the 2 pi on the outside. If we square that, we get 1 plus x squared over 4 minus x squared dx. Now, both of these are involving square roots, so I can basically multiply them together. So this becomes a square root of 4 minus x squared plus x squared. Which simplifies really simply. It's just 2.
But when you sort of like rearrange it,
What's that?
when you sort of like rearrange the curve, doesn't that become an equation of the circle?
Oh yeah, this absolutely is a circle. So, I could square both sides to get y squared equals 4 minus x squared, and then x squared plus y squared equals 4. So yeah, that's circle of radius 2.
So couldn't we just like get the stuff? Oh, we're just practicing. Okay.
Yeah, I mean, there's a canned formula for the surface area on a circle, or on a segment of a circle. So we absolutely could have done that, but yep, just trying to get our hands dirty with this this new technique. Anything else on this one before we move on? Okay. All right, so now I have a parabola, and I want to rotate this around the y-axis. So again, let me draw you a quick graph to help us get our bearings. Oh, and really, I'll just draw the part that I care about or need anything to the left of the y-axis. So I'm going from 1, 1 to 2, 4. All right, so there's the segment I care about, and this time I am going around the y-axis. So let's go ahead and at least visualize the shape here. Okay, so still we're looking at circumference times arc length, so 2 pi radius times ds. So let's try to stay with x as our independent variable. Which means we're going to integrate from 1 to 2. In this case, what's the radius?
Is it x?
Is this time the radius is not f of x, it's just x. So we're going around the y-axis, so the radius for any given value of x is just going to be whatever the x value is. So that's one big difference from what we just did. All right, so, oh, I left off something very important. So 2 pi x ds or the ds is, we are dealing with x as the independent variable, so I want to call this f prime of x squared. What is f prime or f prime squared?
Four x squared.
Yep, in this case, it'll be 4x squared. The derivative, so basically know that you have this function f of x equals x squared, and it all follows from there. Let's take out some constants wherever we can. And now, so one big job has been done, and that is setting up the integral. Got it all in terms of x. I believe it looks good. So how do we deal with this integral? I'm sure u substitution popped in at least one mind here. So 1 plus 4x squared is equal to u, which means du will be equal to 8x dx, or 1/8 du is equal to x dx. So that should be all I need. And then I'm going to set my new limits. So these are going to be, I think 17 and 5. And this integral should be u to the 1/2 times 1/8 du. I'm going to pause here for a minute just to make sure everyone's still with me. Okay. And then if somebody wants to go ahead and approximate these, they can, but I'm going to go ahead and just leave it like this. So I think I'm a little worried that I went through this a bit quickly. Please ask me questions if you have them. Are we okay with how I'm setting up these integrals? I think by now a lot of you are comfortable with u substitution, so I'm not as worried about that, but if there are questions there, I can definitely answer them. So yeah, I think my biggest concern is the way that these integrals are getting set up. So if you have any questions there or want me to explain something further or clear anything up, please let me know. right. So this is gonna be the last thing I do before I take us to a break. But what we just did was handle this with X as the independent variable. Let's go ahead and actually do this for the Y, using Y as well. So for me, I think that the thing to kind of ground yourself in is that you're always looking at this integral. It's always the circumference multiplied by some small arc length. So really, it's just a matter of you representing the radius and the arc length appropriately. So based on whatever the solid is, whatever your independent variable is, whatever your functions are, things like that. So really, in this case, I have the same curve, still going around the y-axis, except now the only change I'm making is I want to re-express this in terms of y. So the integral is going to be from 1 to 4 this time. So x equals 1, x equals 2. Actually, I should not be doing that. Y equals 1. Y equals 4. So still making the same shape, I'm going to revolve this around the y-axis. So in our last example, we said the radius was equal to x. And it still absolutely is. We're still gonna have to deal with the arc length. So I'll just leave that there for now. But we're gonna do this integral in terms of, we want y as the independent variable. So I can't leave x my integral. I have to re-express that in terms of y. So this is going to become 2 pi times radical y. And my ds, I'm going to have to re-express like this. 1 plus f prime of y squared. So any questions so far on the differences that have arisen and where they came from?
No.
Nope. Okay, so from here, I know that I have x as a function of y, which we have is y to the 1/2. So now let's get this derivative. So 1/2 y to the negative 1/2. And if we square that, we get 1 over 4y. So again, we have these two things multiply, or two square roots multiplied together, so I can do some combining there. Then this is more or less optional, but I'm gonna go ahead and do one more thing here. I know that 2 is the same as radical 4. So I'm gonna do this to help me make a few more adjustments. And since we just found this surface area, I'm going to leave this here. I'll just go ahead and stop it there at that simplified setup. If you're not convinced, I would go ahead and complete that integral to see that really you are going to get the same surface area as before. And really the geometrically the shape is the same. So we absolutely should get the same same surface area. Any questions here? All right, I'm gonna go ahead and break us for 10 minutes. So I have 7:52 and I'll see you back here at 8:02. All right, let's go ahead and get back to it. So a couple more examples I want to look at for surface area. And since we're getting to the end of this, I'll go ahead and I'll let you all drive. So how should we start?
Drawing the function.
Sorry, what was that, Colin?
Drawing the function.
So we're looking at the cube root of x. And we only care about from y equals 1 to y equals 2. We're revolving around y-axis. Okay, so got a graph to help us organize ourselves. What now?
We could start the surface area function with
Okay.
From 1 to 2.
Yep, 1 to 2. So in saying 1 to 2, I think we got to go with y as our independent variable. Which is fine. We would just show that you can do it in either direction or in using either variable if you want. Okay. So we're integrating something from 1 to 2. What are we integrating?
Would be 2 pi y cubed ds.
Okay, so let's build it from there. So I think we're correct that the radius is going to be x, but we're doing this whole thing in terms of y as the independent variable. So if y equals x to the 1/3, then that means x equals y to the power of 3. So now that we have this function written in terms of y, we can take the derivative and square it. So then you go from 1 to 2. Any questions about this integral and the way it's set up? I think if we're happy with the setup, it's complete. We can move on to computing it.
Why is it 9y to the 4th?
So let's take a derivative here. So x prime is going to be 3y squared. And then x prime squared is going to be so probably noticing a pattern in a lot of the way these arc length and surface area integrals line up with U substitution. But it's a pretty good weapon to keep using. So if I rewrite this integral in terms of U now, the limits are going to be from 10 to, I think, 145. I think 9 times 16 is 144. All right, so I know I kind of finished that up pretty quickly, but I'll give you a second to catch up and ask me any questions if you have them. But if we're okay with the setup of that integral, then yeah, just using U substitution to handle it. We've gotten a lot of practice with that tonight. Okay, go ahead and move on. I think I'm gonna go ahead and leave this one. All right, so like I said, chapter 8 was going to be pretty quick for us. That was the only two, those are the only two sections I really wanted to look at. So we're going to switch gears and go ahead to chapter 11, which is all about sequences and series. And we're going to spend quite a while here. It's a pretty long chapter and a lot of important ideas to handle here. So let's go ahead and get started. So chapter 11 is all about infinite series and sequences. Section 1 is specifically all about sequences. We're going to cover most of section 1 tonight. We'll have to finish it up tomorrow. So the first thing I really wanted to kind of get a sense of is, and it's just a kind of open question to all of you, what prior experience do you have with sequences and series? So have you dealt with them before? Or is this the first time we're hearing them? All right, let's I'll act as if this is the first time we're hearing of it. So let's get into some preliminary stuff here, definitions and basics. So what is a sequence? It's basically an ordered list of terms or elements. So, I mean, almost always you're gonna be dealing with numbers, but really it could be any list of terms or elements that are arranged in some definite order. Another way to think of a sequence, it's a function where the domain is some subset of the whole numbers. So everything we've done so far this summer has been, continuous functions. So the domain of these functions is either all the real numbers or some subset of the real numbers. Now we're dealing with functions that are only going to be defined on, when the independent variable is 1 or 2 or 3 or so on. So these functions are defined on either the whole numbers, so basically 0, 1, 2, and so on, or some smaller set of that. So basically you're going to see these written a lot of different ways, but typically you're going to see this A term. So basically I'm referring to some sequence called A sub n. And I'll try to make these a little more careful since this is the first time you're seeing it. Typically written in curly braces. And really, so A sub n is the name of the sequence, and this subscript down here, this is the index. Basically, whatever the value of that index is whatever term I care about. So A sub 2 is the second term, A sub 3 is the third term, and so on. So I can either refer to a sequence by just kind of identifying which terms they are. So in that top bullet, the first term, second term, third term, or I can just tell you what the values of the terms are. So 1, 1, 2, 3, 5. So basically, I can either show you the index or I can show you what the value of the term is. Sub notation things. So like I said, curly brackets, that's an infinite sequence. So usually we're going to use n as the stand-in for our independent variable. Just like you typically use x for a continuous function, we typically use n as the independent variable or the index of a sequence. Sometimes you'll also see this notation. So what this means is basically this right here is our, what's the right way to say it? The initial index. So basically I have a sequence that's defined for, these are not like continuous functions. There's some minimum value of the independent variable that this sequence is defined for. It's usually going to be 1. In this case, I'm explicitly telling you that the minimum value is 1. And then the infinity just means that there is no upper limit. So basically, there are an infinite number of terms in this sequence. Sorry, I forgot that was the last bullet. Anybody? I'll give you a couple seconds to catch up here before we do some things with sequences. All right, so let's just, not any harder than it has to be. Let's get the first 5 terms of these following sequences. So this first one, I'm explicitly telling you that the first index is n, or the first index is 1. So basically, the first term in this is when n equals 1, what is this expression inside the curly brackets? What is that equal to? So let's get the first 5 terms here. What's the first term?
1/2.
1/2. And then
2/3.
2/3. And then, yeah, pretty simple. Just keep substituting. One more. And then to show this is an infinite sequence, I will leave the ellipses and end it like that. So next one, I have not given you what the starting index is. So what do we assume it is?
Did we assume that it's 1?
Yeah, we assume that it's 1. So when n equals 1, so let's focus on part of this. What effect is this right here going to have on my sequence, this -1 to the power of n? What's that going to do?
It's gonna just become positive and negative, right?
Yeah, so it's going to alternate. So our first term is going to be -2/3. The second term is going to be positive, specifically. I'm going to write it unsimplified just to kind of show its pattern, but 3/9. Then under the third term will be negative. Be -5/27. And then something positive over 81, something negative over 243. That should be a 4. 4, 5, 6. I don't want to close it without showing that it does continue. All right, this one here, give me the first few terms in that one.
It could be 0.
Yep. In fact, it must be 0. So this one, I need my starting index to be 3. Then a 1, radical 2, radical 3, 2.
Professor.
Yep.
It's just a little weird doubt. So the sequence sort of like exists, but there's no sort of like relation between the preceding term and the succeeding term, like or is there?
Well, I mean, well, there's something that unites all the terms. So all these sequences here, there is basically this is a formula for the nth term. So basically I can use this formula to generate any term I want. Your question was, is a term related to the next term or to the one before it?
I mean, like, it's 1, 2, 3, like 1 + 1 is 2, and 2 + 1 is 3. Like, but that's like each term is like sort of like connected in one way or another.
Yeah.
But this is, but I don't know, like, because if you're taking 0, 1, then square root of 2, it's like 1.414, then it's 1.7 something.
So I could also express this. I could leave these unsimplified and just so in doing that, it makes it more clear that there's a relation between adjacent terms there.
Yeah, but then if it takes a more simpler form, like that relation completely goes. There's no nothing.
So I mean, and you're gonna see as we go on here, it makes sense to express these in different ways. Like for example, here, I could have written the second term as a 1/3, but then you're totally right. That would obscure the relation, the pattern that exists between these terms. So it's in I think on the next slide I'm going to ask us to go the opposite direction, and yeah, if we were going that opposite direction, then simplifying these might obscure the relationships that are there. And finally, this last one here, I know that it starts with 1. And then pi over 6, that should be 1/2. Cosine of pi over 3 should be radical 3 over 2. Cosine of pi over 2 is 0. And then negative radical 3 over 2. And then I think is that 5? Yep. We know that one will just periodically repeat. So any question for obviously I know you can just evaluate these expressions, but in terms of the notation and how we express these, any questions there? All right. So now I'm going to have to go the opposite direction. So I want to write an explicit formula for this sequence here. So let's figure it out. So let's figure out the relationships between successive terms here. And I know I did something wrong. It's right here. Otherwise, this won't work. So this denominator should be 625. So basically what I would like to do is this. I want to set up something that a sub n equals, basically, I want a formula. So how can we start marching towards that? A good way to do that would be this. Let's try to relate our terms to our indices. So I know when n equals 1, a sub 1 is 3/5. A sub 2 is -4 over 25. A sub 3 is 5 over 125, which, as Rios was saying, this can definitely be simplified, or reduced, but I would like to be able to see the relationships that are at play. And it might be helpful if we can do this. Do we know what the next term would be?
$15,625.
So that's
no. I don't know.
Yeah, I think that's the denominator. What's the numerator?
-8.
-8. So if I agree with that being the next term, so it sounds like we understand what patterns are happening, so we should be able to eventually cobble together a formula here. So I can see multiple patterns at play here. So let's just kind of make a list of them for now. So what's one pattern we see here?
The denominator is like 5 to the n power.
So we have denominator is equal to 5 to the n. So let's go ahead and verify that right now. So if n equals 1, 5 to the 1 is 5, 5 to the 2 is 25, 5 to the 3 is 125, and so on. That'll always hold. What else is going on?
N plus 2 numerator.
So numerator equals n plus 2. Yep, I think that makes sense. Is there anything else we have to worry about?
My -1 raised to n.
Okay, then we have to have a -1 raised to n. So let's put all those things together and make sure we're okay. So got -1 to the n because I definitely have some alternating behavior. My numerator is n plus 2. Denominator is 5 to the n. Are we okay with this formula?
Would it be like -1 to n plus 1 or something? Because the first term would be negative if it
Right.
was -1.
So yeah, that's absolutely right. So we know it alternates, but we need to make sure that the right terms have the right signs. So in this case, our first term needs to be positive. So we'll just offset our alternating term by 1 index, and this one should be perfect. Any questions on this one? Right, let's keep on going. All right, let's graph one of these things. So I'll show you a couple ways to do this. There's one that I suspect you'll more gravitate to, but let's look at a one-dimensional plot, basically a number line. So on this, all I'm going to be graphing is a sub n. And we've already kind of looked at the sequence. I know that, so I'll put a 0 here. I know that my first, when n equals 1, I'm going to have 1/2. So I'm going to have basically these vertical hash marks are going to stand in for points in this sequence. Then 2/3, I'm going to have a value. Then 3/4, and this might not be to scale, but that's okay. I mean, really, all I want to do is get a sense of how these points are accumulating. And somewhere over here is 1. Am I ever going to have any values in the sequence that are greater than 1?
No.
No. So the way that I suspect we will prefer to graph these things is, traditional Cartesian plane here. My n-axis is only going to be 1, 2, 3. Let's do 10 of these things. Clearly, all of our terms would be positive. It sounds like at least a couple of you are convinced that I am never going to have terms that are bigger than 1. So basically, from here, I can just kind of graph this thing the way you're used to. The big difference is, like I've said, these you can think of sequences as functions, but they aren't continuous. There is, to say, it's basically this would be meaningless. What is what's the 2/3 term of this sequence? And that doesn't make any sense. You know, n has to be integer values. So when n is equal to 1, I'll have a sub n equals 1/2. When n is equal to 2, I'll have 2/3. So basically, I'm going to have this sequence that it's a little bit like this. And as you correctly said, this thing will never, it'll never reach 1, it'll never surpass 1. But graphing things like this gives you some sense of what the behavior is going to be.
I had a doubt.
Sure.
What would the sum be?
That's actually a deceptively difficult question to answer. So actually, this one's not that complicated, but I am not going to answer the question right now. So I'm sure we'll revisit this, but when we get into sums of series, but yeah.
You know, like it feels like there is a value, but then no, it can't. It feels like there is no value. Like, you know, I don't know.
Yeah, hold on to that that intuition, and we'll see if it pans out. But yeah, we'll definitely answer that question at some point, because it is an important thing to think about. But in terms of graphing these sequences, hopefully we can get a sense of, you know, what the sequences do. So that brings us to the idea of a limit of a sequence. So we've already talked about, you know, limits in other contexts, but what do they mean in this context? Really not terribly different. So a sequence has a limit if, as n gets very, very large, as n goes to infinity, a sub n goes to, and I'm just calling it right now, capital L. Where capital L is a real number. I'm going to make this even more clear by using the word finite. Yeah, a sequence has a limit if, as n gets really big, it goes to a real number. If L exists and the sequence converges, you will, I mean, we talked about this in terms of integrals, and it's no coincidence that the meaning is very similar here. If that limit exists, the sequence converges. So, and one thing to pay attention to, a sequence has at most one limit. So if a sequence converges, it converges to one number. If that limit does not exist, then the sequence diverges. So really, and keep there are really two things that a sequence can do. Does it converge or does it diverge? And really the only way a sequence can converge is if it has a one limit. So this is one definition of whether a sequence converges. I'm going to show you another one in just a bit here, but any questions on this first definition here? So this other more formal definition, and I'm not going to really give any preference to one over the other. I think they're both valuable, but one might make more sense with you, so I'm going to give you both. So a sequence has a limit L if for every, and this is the Greek letter epsilon. So I'm going to go ahead and just show you all the bullets and we can talk about what they mean. So a sequence has a limit L if for every positive number epsilon, there exists some integer capital N, such that for all the numbers bigger than that capital N, the difference between that term in the sequence and that limit is less than epsilon. So basically what that means is, let's say you have a sequence that converges. So if that sequence converges, then no matter how small of a positive number I pick for you, you'll be able to come back to me with, all right, here's this capital N. Every term, all the terms beyond this, and there's an infinite number of terms that have an index bigger than that, they're all going to be within that tolerance of epsilon. So basically, if I can graph this out a little bit, let's say my limit is L. And let's say I have this little corridor here, where this right here is L minus epsilon, and this right here is L plus epsilon. I'll draw dashed lines for all three of these things. So I don't know what this sequence does before N. It might bounce around and do all kinds of weird things. But after this capital N, all of my terms have to be inside this little corridor. So yeah, you can make your epsilon as small as you want, but all that's gonna do is make N bigger. You'll never be able to prevent this from happening. So a couple different ways to look at the convergence of a sequence. Basically, just wanted to give you another option, another way to look at this. So we talked about this. Does this sequence right here, N over N plus 1, does it converge? So we just graphed it out. We talked a little bit about what its behavior is. Do we think that sequence converges? And, as I said, there's two possible outcomes, converge or diverge. So the answer is going to be important, but not as important as you justifying it. So let's get this out of the way. Yes, it does. So the way that you can prove that a sequence converges, basically when you're telling me it converges, you're telling me it has a limit. So if you can prove to me that, if you can tell me what the limit is and prove that that's the limit, then we're good. So let's look at the limit of this one as N goes to infinity of N over N plus 1. Let's do this because I'm allowed to do it. I'm going to multiply top and bottom of this thing by 1 over N. And then that gives me this. 1 over 1 plus 1 over N. And this next thing I'm going to write is going to be a little strange, but that's okay. One thing I can do with limits, you probably saw this in Calc 1, but forgot that it's totally legal to do. I can basically apply this limit, basically respecting all of the arithmetic operations that are going on. So, but I can apply this limit term-wise. So the term in the numerator and the first term in the denominator don't have anything to do with N. So those limits are just going to be constant. 1 over 1 plus something. What's going to happen to 1 over n as n gets very, very large?
Goes to 0.
Goes to 0. So this limit ends up being 1.
Does it diverge?
No, it converges because this limit is equal to 1, which is a finite real number. So I have that's a bulletproof way to prove that this sequence converges. I showed you what its limit was.
But what does it converge?
It converges to 1.
Okay.
So
No. Like what I'm trying to sort of like trying I understand is like th- this sum
oh yeah. So right now we're not talking about sums. I'm just talking about basically a sequence is just I'm just listing the terms
okay.
out.
The term converges to 1. Okay, got it.
Yeah. So as n gets very big, a sub n gets closer and closer and closer to 1. But yeah, the sum is a completely different question. We're not there yet. We got to build up to that. Any questions on this this limit?
For the first part, I'm kind of confused on how come you multiplied it by the 1 over n over 1 over n.
Basically try and this is a pretty common technique and you're probably seeing it for the first time here, but basically what I'm doing here is trying to force these limits to exist, because let's say I go back to this step here and I try to evaluate this, the limit as n approaches infinity of, actually I need to break them down. So the limit as n approaches infinity of n over the limit as n approaches infinity of n plus the limit as n approaches infinity of 1. So this is all true, but it's really hard to think about what happens to this as n gets very large. Because I'm going to have something I have something in the numerator that's going to infinity. I have something in the denominator that's going to infinity. So it's a little hard to evaluate that limit. So if I do this algebraic thing here, which is perfectly legal to do, I'm multiplying numerator and denominator by the same thing, then that makes these, basically I'm forcing these limits to exist.
Thank you.
No problem. So that one converges. So I made use of some limit laws that I'm going to tell you about now. And a lot of these are really intuitive, but these are really, really valuable things to take advantage of. Really, because looking at many simple limits is typically going to be more straightforward than trying to look at a one expression all at once. So let's say I have two sequences, A sub n and B sub n, and they both, now highlighted, I'll underline it in red too, but I need them both to converge. Otherwise, none of the things I'm about to show you are true. And C is just some real number. C is some real constant. If both those things are true, then here are some things you get to take advantage of. The limit of the sum or difference is equal to the sum or the difference of the limits. So, and that's something you just saw me do as I was breaking apart those limits, is I can break them into smaller things, take those limits, and if they both exist, just add them together. So sums and differences are preserved this way. Also, some scalar multiple. So if I'm multiplying all my terms, my sequence by a sub n, that limit is equal to c times the limit if I just take that constant out. So constant multiples are easy to deal with. Actually, the product of the sequences is easy to deal with. If I take two sequences and multiply them all together term by term to make a new sequence, then I can find the limit I can find the limit of the product from the product of the limits. Division works very much the same way. The only thing you have to be aware of is whatever your sequence is in the denominator, it can never equal 0. Sorry, not never equal 0, but the limit cannot be 0. And finally, powers. So long as p is some positive number and this limit is positive, so both those things have to be positive, then basically the power of the limit, so the limit of the power of the pth power of the sequence is equal to the pth power of the limit of the base sequence. So you're going to have to, well, homework and quizzes evaluate limits and prove that sequences converge or diverge, and you'll typically be able to save yourself some time by taking advantage of these things. Don't focus too much on copying them down. These things are they're already online for you to take a look at. All right, so let's look at a new one here. I want to determine whether this sequence converges or diverges. So really what I'm looking at is this, the limit as n goes to infinity of f, n over radical 10 plus n. So the technique I just showed you, I would rely on it. Because really, let's say you try to take this limit now, then you have a numerator that goes to infinity. You have a denominator that goes to infinity. So it might be a little hard to understand what's going on.
Or
So
can we do that rule of that the whole Lopit that rule?
oh, L'Hopital's rule.
Yeah.
I can't really use that here because L'Hopital's rule. L'Hopital's rule is for continuous functions. So what I could do is, say I had some function. I mean, if I gave you this function right here, then clearly this thing is defined for all x's that aren't negative 10. So yeah, L'Hopital's rule is definitely another tool you can use. In fact, yeah, because there's no reason not to use it here. So let's go ahead and do it. But the one caveat I'll give you is that a limit of a sequence is not really the same thing as L'Hopital's rule, but I think I can explain this better with a picture. Let's say I have a continuous function that looks like this. But if you want to think about it, but if I have a sequence that has the same behavior, then the sequence is not defined everywhere where I have this curve drawn. The sequence is only defined where the inputs to this function are integers. But I do know that where x is an integer, the function is going to agree with the sequence. So because of that, I can use this function and L'Hopital's rule to figure out what the limit is. So we already discovered that we have one of our indeterminate forms here. So the
Yeah,
limit,
but our limit is defined like in totally like positive. This one, right? There's no negative 10.
right? So yeah, that's why, that's another reason we can do this. So this limit is going to be equal to the limit as x goes to infinity of x prime over 10 plus x prime. So derivative of x is just 1. The derivative of square root of 10 plus x is going to be 10 plus x to the negative 1/2. Oh, times 1/2. But what is that negative 1/2 power going to do? That is going to give me this. Actually, I can just write this without fractions. 2 times square root of 10 plus x. And what is this going to do as x gets very, very big?
Ultra big, infinity.
Yep. It's going to grow without bound. So what does that mean for my sequence?
Diverse.
It diverges. So, and I'll put some more. This limit does not exist. So the limit as n goes to infinity of n over 10 plus n does not exist. Any questions on that one?
I don't know if you could show us how you're gonna do it without L'Hopital's.
Yeah, so if you want to do it without L'Hopital's rule, what I could do is this. And this technique, it seems, I mean, when I first saw it, I thought it was kind of clumsy, but it's really powerful. It's algebraically totally okay to do. So now I'm going to just, same thing as before, divide by, or multiply by 1 over n over 1 over n. That is going to make this numerator equal to 1. The denominator, I'm going to go ahead and put this intermediate step in, 10 plus n times the square root of 1 over n squared. So is it okay with you that I called 1 over n the square root of 1 over n squared? Just like we had numerous times with our surface area stuff. I have 2 square roots multiplied together, so I can go ahead and multiply the radicands by each other. So then I get 1 over the square root of 10 over n squared plus 1 over n. So from there, can we see what's going to happen to that denominator as n gets very big?
Zero.
Yeah, so basically the denominator is going to go to 0. So that means this limits infinity. Yeah, that technique where you basically reduce your powers of your variables to force those intermediate limits to exist. It's a really powerful technique. So I encourage you to take advantage of it wherever you can. We just did a L'Hopital's rule example, and really that is how I was going to deal with this one. So I'm going to leave this as an exercise for you all, but I'll give you the hint that L'Hopital's rule is the kind of I think the most straightforward approach here, but I'll let you take a look at that, and it's a good one to practice on. All right, how about this one? Does this sequence a sub n equals -1 to the power of n, does that converge or diverge? So if I draw this, so hopefully you can see that if I graph this behavior is going to continue forever. So does this sequence converge or diverge?
Is it
It's
diverge?
just a it's a divert. I don't know.
Yeah, so yeah, it diverges. So one thing to keep in mind of, and I'll go ahead and write this in, if a sequence converges, I'll call it a sub n. If the sequence converges, then you are telling me this: the limit as n approaches infinity of a sub n exists. So as n gets really, really big for this guy, a sub n does not tend to one number. It oscillates indefinitely between 1 and -1. So there is no limit. How about this one here? -1 to the n over n. What do we think about this one?
Does it also diverge since the numerator diverges?
So let's see, if my first term is going to be -1, 1. My first term is going to be -1. My second term is going to be +1/2. And then the next one's going to be -1/3. So my terms are alternating in sign, but what are they doing as n gets really big?
It's going to 0.
It's going to 0. So this one actually converges. So let's make sure of something. So I know that when n gets really large, this denominator is going to get bigger and bigger and bigger. And you're dividing this numerator, which is either 1 or -1. But it's a little difficult to deal with because the numerator on its own diverges. We just showed that. So there's a theorem that we need to think about, and this one is also very powerful, called the squeeze theorem. So here's what I'm gonna do. I have a sub n equals this. I'm gonna bring in two other sequences. This one is just gonna be -1/n. And this one's gonna be +1/n. So here's why I'm bringing this in. I know that this is always gonna be true. -1/n is less than or equal to the sequence I care about. And this thing will be less than or equal to 1/n. So are we okay with the, or do we believe this is true? That basically this sequence in the middle is always going to be between -1/n or +1/n. And really it's going to be equal to one of them, depending on what n is. So let me ask you this now. What is the limit as n approaches infinity of -1/n? And what is the limit as n approaches infinity of +1/n?
Are they both just 0?
They're both 0. So now here's what we have. We have the limit of this sequence is 0. The limit of this sequence is 0. And I have this third sequence that's always in between them. It must also go to 0. So that's what the squeeze theorem is. So and we got like just a couple minutes left. Let me put some details behind that before I let you go. So a couple of theorems that we'll make more use of tomorrow. So first one is the limit continuity theorem, which we haven't used yet, but we'll do some things with tomorrow. So let's say the limit of some sequence is L. And you have some function f, which is continuous at L. And basically I can take that limit of that sequence a sub n, let that be the input to some function, and I can get the basically the function evaluated that limit, or evaluated of that sequence is going to have the same limit as the function itself. So this will give you some leeway and some more leeway in breaking down sequences. And the other one we just talked about is the squeeze theorem. So if you have this situation here, where I have some sequence b sub n that's always, you know, contained. It's always basically in between A sub n and C sub n. And A sub n and C sub n have the same limit, then B sub n has to have the same limit as the other two. So two really powerful theorems that we'll get some more practice with tomorrow. Any last question before I let you all go?
Can we do that? The that question from the exam, the pyramid, sort of like quarter.
Yeah,